Patty Simpson with Simpson Math. In this video, we're going to graph an example of an exponential function. So in this video, we're going to look at this function 2 to the x. We saw in a previous video that in order for it to be an exponential function, we have some constant that is a positive constant raised to the x power. So our input is in that exponential position, and that's what makes that an exponential function. So we're going to graph these. We also saw in that previous video that our x values could be any real number. So our domain can be anything. So we're just going to plug in some numbers for x, and since our x can be any real number, we're going to plug in the numbers, or substitute in the numbers, -2, -1, 0, 1, and 2 in for our x values. So first, I'm going to substitute in the -2. So x to the -2 power. Remember that negative, anything to the -1 power just reciprocates it. So this to the -2 power is equal to 1 over 2 squared. And 1 over 2 squared is 1/4. So when I input -2, we get out 1/4. I'm going to input -1, and I get out, remember that reciprocates it, 1/2. When I put in 0 power, 2 to the 0 power is equal to 1, because any non-zero number raised to 0 power is equal to 1. When I put in 1, 2 to the first power is just 2. And when I input 2, 2 squared is equal to 4. I'm going to graph those 5 points on this coordinate plane. So first at -2, 1/4, -2, 1/4, -1, 1/2, -1, 1/2, 0, 1, 1, 2, and 2, 4. 4. Now, if we look as we get smaller and smaller, if we input smaller and smaller x values, say we put in a negative 10 for our x value. You know, if I were to put in a -10, so way out here, what would my output be? Well, that would be 1 over 2 to the 10th power, because that negative brings it down, reciprocates it, and so then I have 2 to the 10th power. Well, 2 to the 10th power, you know, is a large number. So that fraction is small. Well, if I made this a -100, then it would be 1 over 2 to the 100. That's even smaller. So my fraction, the further out I go along my x values, the smaller and smaller this fraction gets. My output gets smaller and smaller. And yet, it's never going to reach to 0. Even if I put in -1,000,000, it just gets tinier and tinier, but it never makes it down to 0. So we have this asymptote here where y equals 0. So there's an asymptote where y equals 0, so that my graph is getting closer and closer to that without ever reaching it as my x's approach negative infinity. Then on the right, this is growing very rapidly. You can see it's growing exponentially, and we call this exponential growth. This is an example of exponential growth, where my graph is growing very rapidly. Some other examples of exponential growth, well, right now during this coronavirus time, we can see exponential growth within the virus, that as it's spreading, it's exponentially growing the number of cases that we have. So that's an example of exponential growth. So be sure to label your points, kind of like your English teachers ask you to put capital letters and periods on their papers. On your points, you should at least label your axis, if not the points themselves. Notice also that my y-intercept is here at 0, 1. It turns out that on all our exponential parent functions, we're going to have a y-intercept at 0, 1, because when I put in 0, I'm going to get out 1 every time. So there will be a y-intercept on all of our exponential functions there at 0, 1, or at least at the parent of those exponential functions. So what do I mean by parent? Well, remember our transformations? We can use those same transformation rules to help us with any of the family members of this 2 to the x. Now, exponential functions are a little bit different from our other functions in that each one of its family members has its own parent. So in this case, this is the parent, 2 to the x is the parent of 2 to the x minus 5. But the parent of an equation like this, where I have 1/2 x minus 5, that parent is just going to be 1/2 to the x. So those are two different families, or two different parents there. So, but we can use our same transformation rules to help us to graph this function that we used before. So notice this minus 5 is on the outside of my function. It's being subtracted. There's the parent, and it's being subtracted off. So therefore, it's going to affect my y values, or the output. So I know that because it's going to affect my y values, it's going to shift this graph vertically. And those y values are truthful. They do what we think. It's going to just move down 5. So I know I'm going to take my parent and shift everything down 5. So I can do that. I can just take my parent and shift it all down 5, or I can start with my parent function. So I'm going to do that. I'm going to start with the parent function. So the points on my parent function are -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. And what's happening with my points, or those values of the points, is all my y values are being shifted down 5, or I'm just subtracting 5 from each of those y values. So I'm going to take each of my y values and just subtract 5 from each of those. So that I end up with, well, 5 minus 1/4 gives me 4 3/4. But this is a negative. The negative wins out there. He's bigger. So here I've got 1/2 minus 5 gives me a -4 1/2. Here I have -4, -3, and -1. So I'm going to have points on this particular graph at -2, -4, 3/4. So let me put that one on there first. At -2, 4, -4, 1, 2, 3, 4, and 3/4. At -1, -4 1/2. So -4 1/2. Here at 0, -4. There at 1, -3. 1, -3. At 2, -1. 2, -1. And just like before, I can put in smaller and smaller numbers out towards infinity for x, and I'm going to get closer and closer to a value. So look at this asymptote. The asymptote was here at 0, where y equals 0. It shifts down 5 spots. So my asymptote is also going to move down 5 spots. 1, 2, 3, 4, 5. So my asymptote moves down 5 spots. So now I have a y asymptote, or a horizontal asymptote, at y equals 0. So my new function here, using those transformation rules, make sure it has the same shape, looks like this. And again, is growing exponentially. It just took all those points and shifted down 5 spots. So from 0, 1, I moved down 5 spots to 0, -4. Again, make sure you label all of your points in your exponential function. So when we are graphing exponential functions, we're going to take our parent And then we can use those same transformation rules like we did in the past. In the next video, I'm going to do another example where I graph 1/2 to the x. Math Made Simple at Simpson Math. Thanks for watching.